Yeah, so I was introduced as speaking about hydrodynamics in the Carrollian context. However, that was not exactly the instructions I received. So what I received as instructions was to sort of give a pedagogical introduction to hydrodynamics as a whole, especially because I was told that not so many people know exactly what it is. Now, I said yes, and then when I started preparing this, I was like, oh my God, I mean, what have I done to myself? Because it is a huge field, and that really depends on which angle you take, really depends exactly which community you come from. I will not be able to give an overview at all about a field that started maybe with Bernoulli, but I will sort of focus on some aspects that then connect a little bit with some stuff that people have been doing on fractons and also on Carrollian fluids. And I will gloss over so many details that everybody will be annoyed, especially the ones that know a little bit about hydrodynamics. Anyway, so I will sort of do some kind of summary of some of things that I've been involved in the past few years with some of these collaborators you can see here. Circled in red, Akash Jain, Ruben Lear, Emil Heo, and others, on trying to understand a little bit how to formulate hydrodynamic theories with different global symmetries in different background spacetimes, with different geometries, you know, pretty much at almost every scale you can think of, from Planck to cosmological scales. I've been involved in many of these developments, as has many people. So I'll try to say just a few things about that. Now, this is my plan. I'm going to start with just some sort of meta-level idea about hydrodynamics. And then I'm actually only going to focus on some aspects of equilibrium hydrodynamics. And we can discuss non-equilibrium or dissipation, etc., if you want, as we go along. Now, when I sort of speak to at least some people in my field, which I'm more in the community of string theory, high-energy physics, some people, when I say hydrodynamics, they really don't exactly understand what it means, and they think that there's nothing to do about hydrodynamics anymore, it's a 19th century thing. So I just want to say in a single slogan what I think this is, and maybe what other people might think this is. And hydrodynamics is there's an equality sign there. It's low energy, you know, thermal under parentheses. I'll try to say why. Non-equilibrium effective field theory. So if you take this point of view, you might, you know, start to understand that it's pretty much everything, or low energy everything. And it's thermal under parentheses because some people think, you know, the ideas even extend beyond, you know, the finite temperature case to zero temperature, and so on. Now, this is used in many different contexts, and people now think of it, at least many people think of it, as a kind of universal language for low energy, long time, large scale collective phenomena. So any sort of thing that you can coarse grain at large scales and look at perturbations or excitations much bigger than some characteristic size, you sort of end up being able to use this effective description to describe that collective behavior. Okay. Now, typically, people think that this is sort of a large-scale kind of thing. It involves many individual constituents, so you have a system with many interacting particles or anything, and it involves a large number to get to this hydrodynamic regime. But people have been continuously pushing this towards lower number of individual constituents, and there's even some sort of modern biological applications of hydrodynamics that it seems that even works with n equals 12, okay? So if there's only 12 particles, you can still get some kind of hydrodynamic regime going. In the mathematical literature, people discuss this as sort of what's called hydrodynamic limits, how to go from micro interacting particle systems to macroscopic equations like diffusion. Is also connected with stochasticity, large deviation theory, for those who know long time tails, how to correct the large scale behavior at long times. And in sort of a big characteristic of it is that it's meant to characterize deviations away from thermal equilibrium. And again, I put thermal under parentheses because some people think, or some people have sort of showed in many cases that it also works if you're just characterizing deviations from steady states, not necessarily what you would call thermal equilibrium. Okay? All right. So this is a microscopic model, and I just want to say when do you think about using hydrodynamics? I kind of give some hints of it. So microscopically, you can have some system with many interacting constituents. Those interacting constituents can be anything. They can be particles, they can be gluons, they can be rods, they can be people, they can be cars, they can be all sorts of agents. And in statistical physics, we now call this a kind of agent-based model. It has some interaction rules. It could be those dictated by molecular forces, by kinetic theory. It could also just be some interacting rules of avoidance. For instance, birds have to self-avoid or align with others. But the point is that there is some kind of scale in this system, typically in kinetic theory, the mean free path, in which things equilibrate, and you can have some kind of local notion of temperature, of energy, of even entropy. And you want to think about these systems, you have this microscopic system. It can be in different phases, it can be doing crazy stuff, but what you want to describe is the large-scale phenomena, the large-scale collective behavior of this system. Okay? So this is sort of a crude picture of it. You can think of it as this system of many interacting constituents, agent-based modeling, or even some kind of experimental design. People can now build all sorts of metamaterials. So these are sort of individual components that they design the interaction rules, and they can look at the large-scale behavior. Or in certain cases in which this picture that I showed you is a quasi-particle picture, so these guys are interacting and moving around with certain rules. Sometimes that doesn't work for certain phases of matter or for certain materials in which they're strongly coupled, so you cannot really have this picture. And then, as probably many of you know, holography comes to the rescue because it can give you a strongly coupled description of these systems instead. So many insights we've got into hydrodynamics of certain phases came from holography. And what you want to do is to describe the emergent collective behavior of this system. And in sort of a crude way, you sort of coarse grain it into some kind of collective variables. So you have to choose these collective variables carefully. And you sort of arrange things instead of being microscopic constituents. You talk about collective variables such as densities and velocities and other stuff like this. And of course, this works well. I'm sorry that this is not so clear in black, but when this sort of scale of observation L is much larger than a microscopic equilibration scale. So this is also known as the Knudsen number. This number has to be small. Okay. So the trick that you sort of have to think of if you want to describe such a system, whatever it is, you have to identify the collective variables. And these ones are typically just the ones you might have seen many times in textbooks. So it includes the temperature, chemical potentials, fluid velocity, and also some sort of low energy fields, typically Goldstone fields, that will tell you more about the system, which kind of phase the system is in. So if this was a superfluid, this would indicate, for instance, the superfluid velocity. If it was a pneumatic that has spontaneously broken rotations, it would be the sort of preferred alignment director, and so on. So these fields are typically there for different phases. And you can always re-express them in other collective variables, such as energy density or charge density, mass density, in terms of those variables there. So this is something that you either know what the microscopic system is and you have a model that you can try to find these collective variables, or if you're a true hydrodynamicist, you just postulate their existence and you go along with it. Yeah. Why? I think I don't know. I don't know if I can answer that question like in a very sort of clear way, because as far as I know, in many cases in which you can, it's difficult to derive. So it's difficult to go from the micro to the macro. And as far as I understand, there's no accepted, way of how to, especially mathematical way of how to do these hydrodynamic limits in general, or what are the conditions for that to happen. I don't have an answer for it. Yeah. Just an expectation that if the system thermalizes and now you have to go into the things of how and when does it thermalize, then this approximation is okay. But maybe you have a better answer? Yeah. No, sure. This, yeah. Mm-hmm. Yeah. Yeah. No, yeah, I understand. And that's my next slide about the symmetries, but still, I'm not sure if that answers the question of under which conditions this comes about in every single system. But I understand it's an expectation. So indeed, after you identify the collective variables, so this is what Kristen was hinting at, you kind of need to know what the dynamics of those collective variables are. And typically, you can, if you know something about the symmetries of the system, those collective variables will be governed by certain conservation laws for that you can express in terms of the evolution of certain operators that will be given in terms of precisely those collective variables over there. So in another way, you can also see it as the slow and long-time dynamics of these operators here. The most common of them, it would be, if you know that there's conservation of energy and momentum in your system, so this would be just given by the conservation of energy and momentum. And if you know if there's charge conservation or particle conservation, this would be given by the conservation of some current that is then expressed in terms of those collective variables. So you either know something about the system because people have figured out, like QCD or any other situation, what the symmetries are, or like many people have done in the past, you postulate the symmetry and you try to see what happens. And maybe that's a little bit how fractons, for instance, came about. But you should know that this is an effective description. So like I started in the beginning, it's a kind of effective field theory. And this stress tensor, these operators, they get corrected order by order in a derivative expansion that we sort of track down by saying that there is an ideal order part, so this is the zero part, and then there's corrections at higher and higher orders that come with derivatives of those collective variables. So we count the order by the number of derivatives that are acting on those collective variables, and that's sort of the typical idea behind effective field theory, that these derivatives are small and are taken perturbatively in your theory. So this is what we call a gradient expansion. And to do that, of course, there's some sort of, how do you say, there's some sort of choice, because you have to tell me, what are the variables that are supposed to be counted at ideal order, and what are then the ordering, the gradient ordering of how you act on it with derivatives. So there is some sort of freedom there that shows up in different kinds of systems, and that leads to different effective theories. So that depends on what you are trying to describe. This here is the simplest example I'm sure many of you have seen. So this is ideal order stress tensor of an uncharged fluid. It's characterized by an energy density and the pressure as a function of temperature. And then this that you see here is the first order correction, which is described by a bulk viscosity and a shear viscosity. Okay? So the way you do this is that you classify the most general structures that can show up in these tensors, allowed by symmetries in your problem, and you end up with an answer like this, once you take into account that entropy production has to be positive semi-definite. So this is sort of something that shows up in macroscopic scales, is the so-called the problem of the arrow of time, how to derive exactly that this entropy has to be positive semi-definite. There's many cases in which you can start with kinetic theory and derive such a law. This law imposes constraints. So for instance, it imposes that these coefficients here have to be positive semi-definite. And this is true for pretty much all the systems I'm going to discuss here, but it's not true in general. So if you have, yeah, go ahead. Yeah, so each gradient is order derivative, so that, this number I put here, the Knudsen number, has to be much smaller than 1. So this is smaller. So this is how you count. No, it's not explicit here, but you understand by the gradients they come with. Yeah, sorry, this is a gradient term. This I didn't define, but this is a gradient also of the fluid velocity. Yeah, I'm sorry about that. That was, yeah. Now this happens for passive systems, or what we call passive systems, or closed systems. So they always obey the second law of thermodynamics. But if you have an open system, like the typical sort of active systems that people discuss in different contexts, this is not true anymore. So there's generalizations that are needed, and you probably could also think about these open systems in holography and how that would work out. But that's a different sort of topic. Yeah? Oh yeah, of course. Yeah, to close the system, you need to give an equation of state, the function, how this depends on pressure. Yeah, for sure. The coefficients at next order, they will be some whatever arbitrary functions of temperature. Yeah, but here there's always an equation of state you have to provide at ideal order. Yes. Okay, so this was a very lightning review of the simplest types of systems that you find or that you want to discuss in hydrodynamics. Actually, this stuff is known for I don't know how long, but the world is rather more complicated. So there's many phases of matter, if you want to put it that way. There's plasmas, and there's superconductors and ferromagnets and gases and quark-gluon plasma, and this is spin ice and the superfluid and D-branes and active pneumatics. So those are liquid crystal systems. And this thing here, you'll never figure out. This is sort of my artistic interpretation of a black brain in higher dimensions. That, whether it's ADS space that this is put in or whether it's flat space, this thing also behaves as a hydrodynamic system, depending on what gravity action you have. And all these phases and many others that I'm not putting here, including the fractonic phases that I don't have a picture for, except that there is some relation between crystals in that, they are characterized by some symmetry breaking pattern and by some symmetries, okay? And here is a list of, I don't know if you're acquainted with all the different forms of breaking a symmetry these days, but there's unbroken symmetries, there's spontaneously broken, there's explicitly broken, there's approximate, that's sort of mildly broken, and there's pseudo-spontaneous, in which it's bothly spontaneous and explicit. Spontaneous and explicit, but mildly explicit. Okay, so spontaneous and approximate. And then there is all these symmetries that people have been discussing these days: time translation, space translation, these are old ones, rotation, U1, and then there's higher form symmetries, higher group symmetries, dipole symmetries, good for fractons, and then boost symmetries, of all kinds that show up in non-relativistic field theories, like Galilean symmetry and Carrollian symmetry, etc. So there's all these kinds of things, and now imagine that you can play with many of these patterns, and there's multiple systems with multiple symmetries, and with intertwined patterns of symmetry breaking. So, you know, the theories become more complicated than the little thing I showed you there. Yeah. Yeah, I'll give you an example of approximate, and then the pseudo-spontaneous comes in. Okay. So let me give you just some examples for those who don't know. I'm sorry if I'm being very pedantic, but again, I was asked for a pedagogical overview of things. So this is an example of a conventional symmetry. This is a U1. It has a conserved U1 current. I can integrate this over a volume, and I have a conserved charge. Okay. Now, an approximate symmetry is one that somehow there's an operator in the theory that is allowed to inject or take particles out of the system. So the conservation law is broken, but if you see here, there's this curly L there that says, you know, that sort of you fine-tune that curly L to be small, such that the derivative here counts as much as that L. So it doesn't throw out away the symmetry. You kind of bring back, you bring in this operator here that caused the violation into the hydrodynamic regime. And now the theory is approximate in this way. Now, an example of pseudo-spontaneous is one in which this symmetry to begin with was spontaneously broken. It was a superfluid, for instance. The conservation law of a superfluid doesn't change because it's spontaneously broken. The theory has exactly the same symmetry, but on top of that, I explicitly break it mildly. So then that's called pseudo-spontaneous symmetry breaking. Okay. That's how you, in practice, this gives you a mass to your Goldstone field and relaxes the Goldstone. Okay, that's nothing. It's just a symmetry lingo for giving a mass to a Goldstone. Here is the example of a U1 one-form symmetry. Okay, so a U1 one-form symmetry is characterized by a two-form current. So this is a totally antisymmetric current that is conserved. Okay, and one example of a theory with one-form symmetry is electromagnetism. Here is sort of the magnetic field lines that do not end if there's no magnetic monopoles. And you integrate this on the codimension 2 surface in 4 dimensions. So you put a plate here, and you count how many field lines cross that plate. And this charge is, of course, you know, constant under shifts of this surface. So anywhere I go, I will count the same number of field lines, exactly because they cannot intersect, because they're conserved. Okay. So this is a two-form symmetry. It counts not point particles, it counts extended objects. And if you go and add 3 indices, 4 indices, 5 indices, etc., you're adding the dimensionality of your charges in your theory. Okay. Now you can also approximate that. Okay, and this would be the analog of introducing magnetic monopoles here, here, and there that break the symmetry in a mild way in those points there, and you can see the lines can now connect or they can branch out into other lines. Okay. Now, yes. Yeah, I didn't put them in. I should I should add them here. I thought like this morning I'm missing anomalies, but yeah, that's another class of yeah. But here, this one here. Well, I think. Yeah, I think in many cases you can, at least the way we think of it, it could be that the anomaly can generate something, but then we wouldn't call it exactly approximate. So normally when we call approximate is because there's explicit breaking, and that means I just pull out of the hat some operator that breaks it by hand. It's not a dynamical sort of breaking. Then I would call it, there's a kind of anomalous symmetry going on. Yeah. Sorry? Yes. The anomaly will... the anomaly will introduce a null. Yeah. Yeah, it's not a function. Yeah, you can. Mhm. Maybe it would. Yeah, maybe it would in that case. Yeah, maybe. Yeah. Generically, it wouldn't. Yeah. Now, one funny thing about higher form symmetries when they're explicitly broken is that they give rise to an emergent topological symmetry. Because if you see here, this is a two-form antisymmetric current. If I act with another covariant derivative, the left-hand side vanishes, and I get the conservation of L. So this is what I'm showing here. So I have the higher form symmetry, but I act with another covariant derivative, and I get the conservation of L. We call that topological symmetry. And what does that do is that now I can integrate over the whole box, and it will count the number of topological defects. So any higher form symmetry that is explicitly broken will furnish another topological symmetry. And now you can see, if you break one, there's an emergent another one. You can do something with that one as well, and you go on and on writing hydrodynamic theories. Now let me show you some systems besides the one I mentioned of electromagnetism that have these sort of symmetries, because they're really all over the place. They're almost a rewriting of all treatments of people did in classical physics for a while. So this is a lattice, this is a crystal. Typically a crystal is very ordered. It has some discrete shift symmetry. So imagine a perfect crystal without these red dots, the lines wouldn't end. And in that case, a crystal is characterized by goldstones of spontaneous translations. These are these phi I. And they obey this relation because this is a scalar, perfectly regular, obeys this Frobenius kind of relation. And that means that these phi fields, they're level sets that sort of define the lattice lines of your crystal, okay? Now, you can literally just use Hodge duality on this thing to write the Bianchi identity as the conservation law for a two-form. So this is in 3 dimensions. This I just labels each of the goldstone fields. So there is, in 1 + 2 dimensions, there's 2 of these. So there's two of these currents. And you can see that secretly, a crystal has a two-form conservation law. Now, once you introduce a topological defect, which is what this thing is doing here, is cutting the line in some parts, so these are the red dots, that means that this thing cannot foliate any longer a perfectly regular crystal, and that means that the right-hand side is violated by this density here. And now, as you can see, this becomes a sort of approximate higher form symmetry, and the charge that you can compute, because this is conserved, will be the number of topological defects. In this case, these are these locations in this crystal. Okay. Now, there's many other different types of symmetries. This was just to show you what you can do with higher forms. There's a zoo of things. But one that people like maybe in this room is dipole symmetry. So this is the conservation of a dipole moment that you can write here in flat space in this way. And this is the conservation law for a current with, or for a system with that dipole symmetry. And you can see that once you use this conservation law into this equation that tells you whether or not the dipole moment is conserved, it indeed leads to that because of that sort of conservation law. Okay. So these are sort of examples of symmetries that are very different than the traditional case, and some people like to call this exotic symmetries, that make the sort of hydrodynamic description a bit more complicated. Okay. And there's many examples, so here I'm just listing a little bit. So of those kind of symmetry breaking patterns. So this is a superfluid. A superfluid is a U1 spontaneously broken. A pin superfluid is when I explicitly break it as well. So this is pseudo-spontaneously broken. A plasma, the ones that are describing, the plasmas around a accretion disk, for instance, or composing the accretion disk, it's one U1 one form temporally spontaneously broken. I will tell you in a bit what does that mean. You have black brane, so ADS, flat space, you can have all of the above and more. You can cook up sort of symmetry or actions that give you these broken symmetries in one way or another. A superconductor is a U1 one form pseudo-spontaneously broken plus spontaneously symmetry breaking on the emergent zero form that comes from that, from the U1 one form. Fracton fluids has dipole or U1 spontaneously broken and has absence of boost symmetry. And the Carrollian fluid, which people also call, Carrollian fluid that I claim has boost symmetry spontaneously broken is what people have called in the literature a frameit. Okay. Are there any questions or I? Oh, okay. Yeah.
So your definition of Carrollian fluid integrates the boost symmetry.
Yes. But I'll get there at the very end. But
exactly. But already at this point,
is it not? Sorry.
Too restrictive. For application holography, paper that they've shown that in fact, use dynamics of bulk gravity, you need to have assume that the boost symmetry is. But it's not the most general.
No. I can go that. I'll get there at the end. But the claim is that what they have is precisely a case of this. So in their case, the claim is their boost symmetry is spontaneously broken. Okay. I don't know. I think so. Good, you mentioned that. No, I honestly, the pin superfluid, in my opinion, is a toy model. Okay, so the best case of pinning is in a crystal. So instead of being a pin superfluid, it's a pin crystal. So you put this explicitly breaking in the translation symmetry. That gives you momentum dissipation. So that's sort of momentum relaxation. So this is the whole thing of, for instance, if your crystal is an electronic crystal with the electrons, they collide within the lattice and the momentum leaks. If you have it pinned, it means that the oscillations will tend to some kind of reference point, which is typically determined by the number of impurities in your crystal. So pinned crystal is something that models impurities in the crystal. So atoms from other crap that when it crystallized ended there. So that's a good test of pinning, and people look at response functions, and it's really like there's a pinning frequency. But pin superfluid, yes. All right. So I'm going to move on. I'm just going to discuss equilibrium. Okay, yeah, I'm pretty okay. I'm going to discuss equilibrium first in relativistic context and then non-relativistic context. So now I'm just going to tell you how do we construct the ideal order stress tensor of a fluid with a given symmetry, and I'm going to give you some examples of how that is done, okay? So first of all, a fluid doesn't live somewhere, If it's relativistic symmetries you're thinking about, or relativistic flows, then it obviously lives in a space-time that is typically described by a metric tensor, G mu nu. And if it's charged somehow, then it can also have a non-trivial coupling to, for instance, a gauge field. So this would be describing a fluid that is translation invariant and has a U1 global symmetry, okay? I would think of a space-time like this. I have to place the fluid somewhere. It has to be in some kind of background metric and a kind of background gauge field, okay? So let me discuss how I do this for a superfluid. So I think one of the most sort of important developments in hydrodynamics in the past, 3 centuries is the idea of an equilibrium partition function, okay, for fluids. And this was, developed by several people. As far as I know, the first people who came up with this idea, not exactly in this language, was in what's called the Blackfold literature, in which people were putting fluid flows, stationary fluid flows on submanifolds. But then this was developed by Kristen here and collaborators, and also Shirazmin Val and collaborators in 2012. And they put this on a more precise footing of what this exactly means. And I really say it's the most important development because if you don't know how to do this, I think you're always bound to make mistakes on how to write your effective theory for fluids. Okay. So fluid dynamics, as I said, I'm sorry if I'm being a bit rude, but I think it's a true statement. As I said in the beginning, hydrodynamics describes deviations away from equilibrium, global thermal equilibrium, okay? You need to be able to tell me what is your global thermal equilibrium first, before you can describe deviations away from it. A way to do that is to construct the Euclidean partition function, thermal partition function for your system. So this is the partition function that is given in terms of some sources. So in this case, it's G mu nu and mu, sorry. And it's an integral over your light fields, so your Goldstone fields. In this case, I said I'm only talking about the superfluid, so I have one Goldstone field that breaks the U1 spontaneously. And then what is here written is what we call a hydrostatic effective action for the system in consideration that depends on these sources, G mu nu, A mu, and the Goldstone field. Okay. Now, this action, here, hydrostatic effective action, has to be invariant under all time-independent transformations of the theory. Okay, it has to realize the symmetries of your system, and in particular, in this case, it has to be invariant under diffeomorphisms and gauge transformations. Okay. There should be an exponential. I'm sorry. Yes, okay. I will go back in the recording, edit the recording, put the exponential. Because it's... anyway, it was late last night. So, if you have this hydrostatic effective action, you can perform variations of, you can perform generic variations of this hydrostatic effective action as you would perform the variation of any effective action that depends on those sources, okay? And you call the operator that couples to that source, you call it stress tensor. This is the current. And here, this is sort of placeholder for the dynamical equation for the Goldstone that you have to set equals to 0. So that's a dynamical field in the theory. The others are background sources, okay? Now, everybody knows, but I'm putting here just a summary of how do these objects transform with diffeomorphisms. They transform with a Lie derivative, as you can see here. And under gauge transformations, the gauge field transforms like that with the gauge parameter, and the Goldstone like that with that gauge parameter, okay? If I just want to know what kind of global symmetries this action realizes, I put in those transformation laws for each of the symmetries, and I'm going to get these conservation laws that you see here. So this is conservation of stress. On the right-hand side is the Lorentz force. Here, the conservation of the U1 current, and this is just the equation for the Goldstone that now it's totally abstract, okay? So this is just a way of parameterizing your effective action, but now I need to actually tell you, what is the effective action? How do I build the effective action? Okay, so the effective action, it depends on this concept of a thermal observer, or a thermodynamic frame, that is defined by vector k mu and a specific gauge parameter lambda k. And it has to satisfy these equations. So under this transformation of a diffeomorphism and a gauge parameter, this special frame has to annihilate those transformations. So this is basically choosing a sort of special reference frame, a time-independent reference frame or observer in your system from which any time-independent transformation won't affect the state of the system. If you want to know more physically what this means, what I'm trying to find is all the equilibrium states, all the time-independent equilibrium states of your theory. So I'm literally trying to find a solution of these equations that is time-independent for arbitrary sources. I do that by finding this special observer. Okay. Now, once that is done, once I find a special k and a special lambda, which, by the way, if you recognize this equation, it just means that k is a Killing vector field, and that so the observer is following a Killing vector field, meaning that indeed everything is independent with respect to that. It's a time-like Killing vector field. Once you find this specific value of k and lambda, you can construct invariants under this theory, under these transformations. You can construct scalar invariants under these transformations. And one of them is the sort of your Euclidean time circle. So this is the temperature, which is basically the modulus of that Killing vector field over there. You can think of it as just the time component of your metric, if you can relate to that. And you can also build a chemical potential using both the Killing vector and this lambda parameter here that you fixed. I unfortunately didn't say this here, but the U is given in terms of the Killing vector as well. So the fluid velocity is just this, okay? So everything here is given in terms of those parameters and the metric sources. Yeah. It's local, it's a gauge, it's gauge, yeah. A mu is a background gauge field that transforms under a normal gauge field. Sorry, say again? You can gauge fix to get rid of it. No, I don't want to do that. No. I wouldn't know what that exactly would. Yeah. Right. No. That's. It's not an arbitrary function of space-time. No, that. It is an arbitrary function, yeah. But it's not. But the field A has no dynamics. I think this is what. Yeah. I can get rid of phi. Yeah. Right. Yeah. I guess I would have to gauge fix the source somehow. Yeah. Yeah. I don't think anyone tried to attempt that at some point, but yeah. 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 Okay, so let me go back here. So there's another invariant that you can build out of these fields. So this is the superfluid velocity, precisely because of that transformation, okay? And you can build this scalar invariant that is just the square of the superfluid velocity. So you can see here, there's this 3 sort of scalar invariants that your partition function can depend on that respect all the symmetries. So this is what it takes just a very simple form in which the pressure is, we call it the pressure because you can identify this with just some thermodynamic arguments with the pressure. And it depends on the temperature, the chemical potential, and this scalar that I call there chi, okay? Now, what is the usefulness of this is that I can vary this and obtain all the equilibrium currents of this system. So if I just vary with respect to the metric, I get the stress tensor of a superfluid. If I vary with respect to the gauge field, I get the current of a superfluid. And if I vary the whole thing with respect to the Goldstone field, I get what's called the Josephson equation that gives dynamics to the Goldstone field. These functions here that you see, f and q and e, they're defined as thermodynamic derivatives of that pressure and obey these kind of relations here. Yeah. Yes, it does, but in equilibrium it's the same as mu. Yeah. Good point, yeah. So you have to see what are redundant ones. There's more choices in this, yeah. I am in equilibrium and I'm focusing on time-independent transformations, so I'm, yeah. No. But you know, I didn't mention this, and this, again, it's a very naive, very lowbrow review of hydrodynamics because there's a whole different machinery called the Schwinger-Keldysh effective field theory that can lift all the statements that I'm saying to complete dissipation, time-independent dynamics. But, you know, yeah. Actually, I don't exactly know. I never know the distinction between Eulerian and Lagrangian frames, but I don't think it is. But do you know, Ristan? I don't think. Yeah. 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 Definitely. I don't know if there's a notion of Eulerian frame, but there's definitely you can definitely write some sort of action with Eulerian coordinates if that's what you mean, and you introduce some scalars, etc. That's a different story than this here. Yeah, if that's what you meant, that's a different story. Yeah. I just want to briefly say what's the unrealistic pin superfluid that Kristen mentioned. So this would be going to this effective action and adding a mass term like that, in which this scalar field that I'm putting in, I'm just putting it by hand as an additional source in the theory that models precisely this kind of approximate symmetry. And what happens, as you can see here, is if I write the full Josephson equation, including time dependence as well, so I went a little bit off equilibrium here to write this equation. On the right-hand side, I get a mass term for the Goldstone that then would be responsible for relaxing this dynamics. And it has certain defects, this sort of mass term that appears there. For instance, the linear spectrum of fluctuations won't be a typical sound mode anymore. You can see here is a square root with this thing called the pinning frequency. So it has some sort of effects on on the theory, on the phenomenology of the theory, and that's why people are interested in this kind of breaking. Okay. Let me give you an example of one-form fluid. Okay. So now instead of How do you know? Because there's another way of doing it, which is let's, well, first of all, let me go to the textbooks of Landau and Lifshitz and see if it matches what they come up with. But there's also a different way of constructing the theory, which is just at the level of the equations of motion, writing the most general current and stress you can have given the symmetries. You can just write down adding arbitrary coefficients. You have the conservation laws that does an input to your theory, and the second law of hydrodynamics, and you can go through that process and check that it matches this. So that's another way of doing it. Or you build this Schringer-Keldysh effective field theory that also spits out in general, including time dynamics. So there's different ways of checking that this is right. So let me just briefly say a one-form fluid. I mentioned this because this is sort of a case that shows sort of the idea behind this is shows up in fractons and Carrollian fluents, at least from my perspective. So here, instead of having a U1 gauge field, you have a two-form gauge field that couples to your two-form current. So the effective action is pretty much the same, except that it's parametrized like that. And now I need to find a thermal reference frame by now trying to find a vector k and the lambda k mu that has an extra index there. Okay, so because the gauge field transforms with a one-form parameter, not with a scalar. Okay, so if I try to find this lambda k that satisfies this equation equal to 0, which I forgot to put in, I can find two scalars. One is the temperature like it was before, but this chemical potential here that we call one-form chemical potential is not invariant under these transformations lambda mu. And there's absolutely no way that I can make this chemical potential or construct any other scalar that would make it invariant. There's just no way out of that. And that means that if I only have this temperature here, I will never be able to generate a non-zero current J mu nu because nothing couples to A mu nu if I don't have this extra scalar. Okay? So people were a bit puzzled about this. How do I create a fluid theory with a one-form symmetry? And then the point was that, this is a signal that this phase, as it is, if you don't introduce any light fields, you cannot realize it, at least hydrodynamically. So you have to introduce a Goldstone field. Okay. Now, because the Goldstone field of a one-form symmetry is a one-form gauge field, like the photon, there's some components there, right? It's a one form. But because you're in thermal equilibrium, you have a preferred vector k mu that allows you to break the symmetry only along the time direction, like this. You can introduce a Goldstone field that if you have broken the full symmetry would just be the time component. So here, you can see here, if I had broken the full symmetry, I would just have one time component by contracting with u, which is k. And I define that field that transforms in this specific way, all right? So this is what we call the temporal symmetry breaking, because I'm just breaking along the time direction, all right? So this is something you can do with one-form symmetries that you cannot do with zero-form symmetries. And once I break it in that direction, I can build these invariants here, which is mu, the chemical potential I had, minus T grad of phi. And this is a perfectly good invariant under all symmetries. This is normalized to 1, this h mu. I just broke this up into a modulus and a normalized vector. And now I have an effective action that depends on two parameters, a temperature and the sort of one-form chemical potential that is hiding there. And if I generate equilibrium currents, I get the equilibrium currents that people have been writing down in textbooks for magnetohydrodynamics for more than 50 years ago. So this is a sign that you can play this game to try to see, what kind of symmetry is broken in your system and how to realize it. And this is a little bit how, at least myself and some of us thought about this also in the context of fractons and Carrollian fluids, as I will try to discuss a little bit now if I have time. Can you tell me if I have time? Okay. There's no other way that I know that will realize the one form or even higher. This it's not just for one form, it's for any U1Q form. You need to break it temporally or you cannot write anything. Lambda mu, sorry. If lambda mu is a gradient of a scalar, right. It doesn't change anything. Yeah, no, that, because the transformation of whatever gradient of the scalar won't affect. If it should affect, I don't know how it would affect. Because lambda mu would be the gradient of, but sorry. So here we're talking about this lambda mu, which is the arbitrary transformation, right? Here is the thermal, it's a special one, yes. Okay. So this is still the arbitrary transformation, sorry, this is still the arbitrary transformation here. Could be a? No. I mean, it's a good point. I don't know. I don't think I've. Maybe we can talk afterwards. I'm sure I can invalidate it. Yeah. Yeah, but I can think of it. Yeah. Okay, so I'm going to go to non-relativistic. So now the idea is the same, except that, as probably many of you know, I don't have a space-time anymore. I have some structure, some space-time structure here that I'm describing as tau mu. You can think of it as, people call this a clock one form. And here a ruler, a spatial ruler. You're not allowed to call it a metric. And here there's a gauge field B mu that I changed. Typically, when I'm talking about Newton-Cartan geometry, this is what people call a mass gauge field. Comes from the Bargmann algebra. And here this A mu nu is a symmetric tensor gauge field that people introduce when discussing fractons. So I'm going to treat the whole system of Carrollian, Galilean, fractonic, what am I missing? Aristotelian in one go, okay? So Aristotelian and Carrollian, or well, I should, and everything else, is characterized by what I mentioned before. It has this clock one form, but you can introduce the inverses of these structures. So this is the inverse of the clock one form is this vector V mu that is normalized in this way. You can introduce Vilbines in which this A is sort of the space, the local indices, depending on what symmetry you have, whether it's Carrollian, Galilean, etc. So these are normalized to zero, you can see, so they're orthogonal to each other. The Vilbines, if you contract them, they have a Kronecker delta in there. And then you can build the rulers by just contracting the Vilbines, okay? So this is a structure that is common to Aristotelian, Carrollian, Newton-Cartan, and fractons, okay? If you're in Newton-Cartan and fractons, you will need this B mu, okay? So Newton-Cartan has this mu is the mass gauge field. And if you're in fractons, you also need a mu nu. So fractons needs everything. Aristotelian and Carrollian just need these ones, and Newton-Cartan need these two here. Okay. Yeah, they can appear. Let me. If I'm doing Newton-Cartan, Aristotelian, and Carrollian, I can consider everything, including a beam U, if I want. But that just means that my Aristotelian and Carrollian fluid is also charged. Okay. While for Newton-Cartan, I don't have that choice. This B field is there because it's part of the. It comes out by gauging just the Bargman algebra. Okay. You have, yes, exactly. So I can use it, but if I was a Puritan, if I just want an uncharged fluid, then Aristotelian and Carrollian is just this, and I don't need the rest. Galilean? You mean massless? Is that the issue with the massless, or because now here I'm in the Bargman situation? Galilean? Sorry. Okay, but then wait for a second. Yeah, so here I'm. Yeah, okay, but wait for the next slide. So here I'm just talking about the structures. Okay. Now, depending on the symmetry, these fields will transform in a different way. Okay, this is how they transform. So, sorry, yeah.
Yes, but I think that the structure is not correct.
Okay.
No, sorry.
Yes, okay.
You defined it as, we can call it a metric, so H mu and tau. But there is nothing invariant about tau.
Oh, no, that's over here. Look, tau transforms with the boost.
Yes, but please go back 2 slides before.
Yeah?
Again.
Here?
Yes. So you should replace the tau by V.
In that sense, yeah.
V can be defined in an invariant way up to a scale.
Oh, yeah, sure. So I was not being precise about which of these are invariant in which symmetry. I just said, blah. But I should have, no, sure, I agree with you. So you don't take this at face value, okay, all right? So this is what is important, is the transformation properties of these guys. Yeah. A what? Yes. Yes. You have, well, if I remember correctly, the paper from Jelle Hartong, you can come with an MU field, yes. Yeah, so I think I'm not a Carrollian expert, but there's many faces of Carrollian spaces. The one I'm studying here, which is this minimal one, is kind of the one that you get by taking the C to 0 limit of general relativity, at least in certain contexts that I'm familiar with, and nothing else shows up. But there's an expert here, maybe you know more about this? No? But that's my take on this. So, but there's more extensions of this, yeah. Okay, so in Carrollian geometry, like it was said, the tau is not an invariant, so I should have used the V in my slide. The upper metric is also, the upper ruler is also not invariant. In Newton-Cartan, the V is not invariant. The lower one is also not invariant. The mass gauge field transforms with the gauge transformation, but also with a boost. And then in fractons, B transforms with gauge transformation and also a dipole shift, is this lambda here, and so this sigma, and the symmetric tensor gauge field transforms with the gradient of sigma. Yeah, and if I'm in Aristotelian and I'm considering The B field as a charged field, as a gauge field, it just transforms with gauge transformation, okay? Is this okay for all the Carrollian experts? Yeah. Okay, so what do you get from putting in these things into this action? All right, you get a diffeomorphism or a conservation law for the stress tensor. The stress tensor is defined in that way. All right, you get a U1 conservation law if you just do the gauge transformation. If you do the dipole transformation, you get the dipole word identity. If you have Galilean boosts, the boost word identity for Galilean boosts is this thing here. And if you have Carrollian boosts, is this thing here with the energy current. So this tau mu is called energy current. This is spatial stress, or, well, stress tensor. Without the energy, just stress tensor. And you, yeah, so these are the word identities. Sorry. Yeah. No, I didn't, but I could have to just complete this to the BMS. But I didn't do it here. But yeah, I could have. Sorry. Yeah. No, but it kind of does, yeah. If you write it in components, it's what. Sorry. You have to put this into this, and then you get it. Yeah. Good point. Sorry about that. Yeah. It's what? Sorry. Yeah, it's an independent. It's an independent law for the dipole symmetry, and it's the combination of the U1 and the dipole that gives this the dipole conservation law that people write down generally. Yes, that's true. Yeah. Okay. So, very lightning review. I can precisely play the same game of finding thermal observers in Newton-Cartan, for instance. I'm going to go this quickly because this is just a repetition of what I've been saying before for relativistic flows. So in Newton-Cartan, you actually can construct two invariants. One is the temperature. The other is this chemical potential here. These are the only two invariants you can construct. This is the equilibrium partition function, the hydrostatic action for this. And if you vary this hydrostatic action, you get the currents of a typical fluid, Galilean fluid that you find in normal textbooks. So people have checked this very much. So that's one case of what you can do with Newton-Cartan. But the other ones are slightly more interesting because they're things that people hadn't really considered before. This is the case of an Aristotelian fluid. You can write three invariants if you include the charge, the U1 gauge field. You can write the temperature. You can write basically the square of the fluid velocity, so that becomes a thermodynamic parameter, the fluid velocity itself. And you have also a chemical potential. So now the hydrostatic effective action depends on these three coefficients here. Now, an interesting thing about this sort of Aristotelian case, in which, by the way, if it was not clear before, Aristotelian case has absolutely no boost symmetry. There's absence of boost symmetry. Nothing transforms with boosts. You can compute what's called the sound modes. You perturb your fluid equations away from equilibrium, you solve them, and you find the spectrum of excitations. And what you see here is that this is the frequency of the excitation, this is the momentum, is that there's actually two sound modes. Typically, when you do it for a Galilean invariant system or a relativistic system, there's a pair of sound modes, but they have equal velocity. The difference here is that they don't have equal velocity precisely because there's no boost symmetry. So the boost symmetry ties these two together, but in the absence of boost symmetry, if you have a preferred velocity in the system, which is given by this U here, in equilibrium, then there's a difference moving in the direction of that velocity or moving against it, because there's no boost symmetry. So this is sort of an interesting aspect of Aristotelian fluids that yeah, sorry. is a killing vector of the geometry. Yes. Sigma k would be the, sigma, I changed the lambda to sigma k when I went to the mass, so this would be the transformation of the gauge field. Yeah, for Newton-Cartan has to do with the gauge field, the mass gauge field or whatever. But for in the Aristotelian case, it would be charged, a U1 charge. Yeah. So this is Aristotelian. I'm definitely going. I think you have to stop me when it's time to stop. Okay. Now, let me look at the fracton fluid. Yeah. It be measured? Yes, because so this, so this is more relevant for soft matter or active matter when you have this, for instance, a flock of birds, self-propelled flock of birds. You can that is moving with respect to some reference fluid, which is the air. Or you can think about bacteria, collective bacterial motion on a fluid that is fixed, for instance. So there's a fixed reference frame, which is velocity. So boost symmetry is absent completely, and there you could measure these things. Yeah. But so high energy, I don't know if there's any application of Aristotelian to high energy, but. Yeah. So for a fracton fluid, you have the B field and you have the A mu nu field, and you could try to construct a chemical potential like one does for the other ones in the other cases, but this chemical potential is not dipole invariant, precisely because the gauge field transforms with the dipole shift. Okay, and the problem here is very similar to the one-form case, is that there's no way I can construct an invariant chemical potential that is going to give me a non-trivial current for my fracton fluid unless I introduce some light field somewhere. Okay, so I'm not sure if you have heard these statements in the literature before, but for fracton fluids, at least for fracton fluids, maybe Kristen tomorrow has more cases of this, the dipole symmetry or the U1 symmetry has to be spontaneously broken for you to have anything in this macroscopic regime. Okay, so people have discussed two types of fluids, two types of breaking. P-wave superfluids, the dipole symmetry is spontaneously broken. So you have a kind of dipole Goldstone field, which is this psi mu. Or you have an S-wave superfluid, in which the U1, you break the U1, but that automatically breaks the dipole symmetry. And in this case, you have a specific, in principle, you could introduce two Goldstone fields. And in general, or in the low energy regime, these two guys, they get tied together. So it's only a combination of them that actually makes sense. I call this the U1 low energy regime, but you can play around with the effective action by adding this mass term and the scale that somehow keeps the two of them in the game. So this is like playing this approximate symmetry kind of game with these two Goldstone fields. And it's possible to have sort of a pinned regime of these S-wave superfluids. Okay, so these are sort of the possibilities that people have explored here. So let me go through very quickly, just to know I have 10 minutes or something, right? Yeah. Okay, so maybe I'll just explain one and then I go to Carroll, otherwise I won't reach Carroll. So if the dipole symmetry is spontaneously broken, so this is the P-wave case, there's a Goldstone that transforms with the dipole shift. And you can construct pretty much some kind of analogs of superfluid velocities, as in the other situations I showed you, by combining these invariants of the background fields and the Goldstone fields. So this structure here, mu nu, is invariant, very much analogous to the superfluid velocity of a normal superfluid. And with the dipole field, you can also construct a sort of bona fide gauge field that only transforms under gauge transformations, but not under dipole shifts. Okay. Now, in fractons, the story is slightly more complicated in terms of gradient expansion. So you have to be try to be clear about what the gradient expansion is, what fields are ideal order and what fields are not. And here it seems that there's some consensus that there's only one choice for these p-wave superfluids, in which these fields are treated as order 1, so these are ideal order, and the dipole field is treated as order -1, so that the gradients of the dipole field are order 1. So this is the typical scaling of all other superfluids that people had thought of before fractons came to be. Yeah. Well, I'm using ideal order as 0th order, but you can be picky about that. I agree. Now, this, there's a bunch of scalings that happen to be necessary for this to work. So the spatial part of these fields have to scale with order -1, and time derivatives have to count as order squared. So there's some kind of anisotropy in the way you treat both space and time. I don't want to delve too much into it because I imagine one of the speakers afterwards will take care of these kind of issues. But the point being that once you introduce this field, you can actually construct a p-wave chemical potential that is invariant under all symmetries. And requiring that chemical potential to be order 1, it means that your flow has to be small, has to be gradient suppressed. So these fracton fluids, they flow, but they flow very slowly. That's sort of the mantra here. And you stick this into a partition function, and you extract the currents of these fracton fluids that have agreed, or agree with all the other sort of constructions that people did before in different ways for what these fracton fluids would be. Okay, so before I go into more details, I think I'm going to skip all this. I'm sorry about that. I'm going to go to Carrollian fluids, okay? So let me discuss the Carrollian case a little bit. So here, as was pointed out, the tau field is not invariant, so it transforms with the Carrollian boost, and the upper ruler as well. I can try to construct a temperature. I can't. The temperature is not boost invariant precisely because the tau field is not boost invariant. So that's a problem.
Yes, but what about K mu?
Sorry?
What about
K mu doesn't transform under boosts. It's a Killing vector field. Sorry? I mean, I think I'm not sure if it's by hypothesis. It's more, what's the definition of a Killing vector? Or what's the definition of a Killing vector field? Yeah, that's true, but then there's no flow. You see, because if I aligned it with, that's a good point. You could say, oh, but my Killing vector field is only aligned with time direction, but then I have no fluid velocity. Because, why? Because the fluid velocity is the spatial components of the Killing vector. So the UI would be Ki. But if I have no Ki, there's no flow. So that same thing you said, you could actually, sorry, I'm not going to go back, but you could actually do for fractons. You could demand that there's no flow and then try to do that, but then, it's not exact, you won't reach Fluid velocity? No, I mean, I don't know, which case are you talking about? Sorry. No, but Carrollian, but coming from where? Like the fluid velocity there, what you call fluid velocity, is not Carrollian invariant. It's not boost invariant. I don't know if I wrote it down here, but this is the fluid velocity relativistically, okay? You can write this in terms of sort of time-like Vielbein that also gets corrections in c squared. And then, if I'm not mistaken, is a plus or minus c squared, and then what you call fluid velocity here. This is what you call fluid velocity by the Carrollian fluid velocity in this relativistic literature. Okay? You agree with this? Sorry? But the V mu is just the frame field. So this depends on the background V mu plus c squared, something else you can define, plus blah, 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 blah. Right, so this is the geometry that's coming from here. This is the dynamical part, so this is the fluid velocity that comes from the relativistic fluid velocity. This is the dynamical field. This is not dynamical. I cannot call this a fluid velocity. I can call this a fluid velocity. But this is not Carrollian invariant. Because this whole thing is invariant under Lorentz transformations, Lorentz boosts, and for this combination to be invariant under Lorentz boosts, this whole thing has to transform in a specific way under Carrollian boosts for this whole thing to be invariant. And that demands that this transforms. Okay? Yes. I should have removed the arrow, I'm sorry, but here, yeah. Sorry? No, because first of all, I cannot even define a U here yet, precisely because I cannot define the temperature. And, and typically, the fluid velocity in non-relativistic theories is the K mu divided by normalized by the temperature. But I cannot define that because I don't even have a temperature. Okay, so this is the problem of Carrollian boosts. Yes. Yes. I don't. I mean, people have, but I don't. Yeah. Yeah, but V mu is the Vielbein expansion in the time component. Okay. And this is the fluid, is the other part of the fluid velocity that you decompose. And this is what people typically call the fluid velocity when they take the C to zero limit of relativistic fluids. They call it fluid velocity. I don't call it. You can see here in a second why I don't call it. Okay. I don't call it because, first of all, I cannot construct this temperature. So I have to introduce a boost Goldstone field. And what I mean by that is a Goldstone field theta that transforms with a Carrollian boost. Okay. And once I do that, I can define an effective Aristotelian geometry by playing around with the theta field. You see, I define a new T hat that is boost invariant, a Vielbein that is boost invariant, and all the rulers are boost invariant. So, yes?
Yes, but introducing this theta is not... Because you already have this tau mu with the Schmann connection. On the local Carrollian boost. Okay, I will fix my local in the broken case. What's the need to introduce this?
I mean, so this theta is a dynamical field, first of all, right? It's not, it's a Goldstone field. It's,
tau as well.
no, tau is not a dynamical field. I mean, it's tau, well, if you give it dynamics in general, in Carrollian gravity, then it's a dynamical field. Here, I'm not taking anything dynamical. These are background fields that the fluid couples to, okay?
Okay, but that's precisely because you impose that your tau field is not dynamical, then you introduce a dynamical field, that you are making your tau dynamical.
But
Because
Okay, maybe we. No, but look, maybe we can discuss it later. But you know, I'm trying to solve the problem of describing the equilibrium global state of a Carrollian fluid in the fixed background. There's a different thing that you can also do even relativistically, which is, you know, how do I couple a fluid to a dynamically evolving space-time? And that's a totally different game than what I'm showing here. Okay, so that's a different.
Yes, exactly.
So here, the geometry is fixed. The Goldstone is a dynamical field.
Okay, but when you say geometry, it depends if you consider part of geometry or not. Carrollian structures, you don't need the tau is a field. For instance, you recover all the field, or you can say, okay, no, I'm working with the ruled Carrollian geometry, and then I fix the tau. Then you have to introduce the will again transform. So defining transformation that acts towards the diffeomorphism and the compensating.
Well, maybe I can hear that you know more Carrollian geometry than I do, but maybe we have to discuss that later, because even if I don't have the tau in my game and I just introduce the theta, that won't help me. That I know, right? I mean, I need, if I'm going to transform.
Sure, to define
yeah, but I can. Sorry. Yeah. It's okay. Yeah, go ahead. Yeah. Go ahead. I'm in the end. I'm in the end. Yeah. Yes. Yeah. Yes. Yeah. Yeah. So I don't know. I literally don't know. What I did know is that there has been many claims in the literature of Carrollian field theories that partition functions are not well defined, that not even fluids were well defined. You know, okay, I mean, you can disagree, but you know, what we tried to do here was to show hydrodynamic limit, we can have something well defined. Now, whether that informs you something about the microscopics or not, maybe that's more something that people here should think of. Yeah, so now I have a partition function. I have my Carrollian currents, stress and energy current and stress. And I also have a ward identity, which is the Carrollian boost ward identity, which is this. Okay, so let's just focus on this this is the last slide. Let's focus on this. There's two, the Carrollian boost symmetry requires this to vanish. Okay, there's two possibilities. Either this thermodynamic function vanishes, or the fluid velocity vanishes. Before this work, there was two types of Carrollian fluids out there in the literature. One that imposed this, and one that came with that. Okay, and now this partition function that I showed you recovers both. So both of them are examples of Carrollian fluids, but this one is the one that comes from the C to zero limit of general relativity. Okay. So the one that sets U to zero is the one that comes from general relativity. And therefore, the identification is that this thing that comes from the Lorentzian fluid velocity, this guy has to be identified with the boost Goldstone. Okay? Because it precisely transforms like a boost Goldstone field. So it's not that things changed very much, it's just a reinterpretation of stuff. Yeah, there's some, you can compute some spectrum of fluctuations. This doesn't, you know, has only a non-vanishing contribution if you have flows that have a fixed velocity to begin with. So equilibrium flows with a non-zero initial velocity. The other one seems to have this regime that comes from general relativity, seems to have a more trivial spectrum, even when you include all the 12 transport coefficients that you can at first order when you include dissipation. it seems to have a more trivial spectrum. But there's, I think, loads of things to be explored here. Also, more detail of how people took the limits also beyond ideal order from general relativity. So I'll just stop there. I'll stop.